this is screencast 3 of chapter 7. Uh, 7 actually first screencast of chapter 7, and in total third screencast. And in this one I'm trying to prove the Newton's second law, F equals to ma by Euler lagrange equation. And to do that, at first I had found the function L, which is T minus B, where T is the kinetic energy and B is the potential energy. Then it is written in Einstein notation form: 1 by 2 mass times velocity square, which actually this is the sum of x velocity square plus y velocity square plus z velocity square minus the potential energy. And now we are now taking in only one coordinate axis. Let's say x of I could be 1, 2, 3. x1 would be x-axis, x2 would be y-axis, and x3 would be z-axis. And here the partial derivative of L with respect to x minus d by dt of d partial derivative of L with respect to x dot of I equals to 0 is the Euler Lagrange equation, which is what we will be using to prove F equals to ma. So at first, trying to find the value of partial derivative of L with respect to x of I is equals to, since there is no x of I, it would be, this term would be 0, and the partial derivative of u with respect to x of I is force in I direction, since force is the negative gradient of u. Now trying for the expression inside here, dl by dx I dot equals to 1 by 2 mass times 2xi dot would give us the momentum in that direction, and derivating that with respect to time would give us acceleration in that direction times mass. So using the equation, now using the Euler Lagrange equation, this term which is equivalent to f of I minus this term which is equivalent to mx double dot I is equals to 0, which just taking mx I double dot equals to on the right hand side, I'll give force in I direction is equals to mx I double dot, and this is true for all other direction as well. That's why we could generalize it as F equals to mx double dot equals to ma. Hence proved. That's it.